All right, so up to now, we have talked about vectors and did a lot of algebraic work with these vectors. All right, now we're going to focus on adding some geometry to our vector studies. Okay, so we're going to look at what's called the inner product, which some of you may be familiar with already, depending on what other math courses or other science classes you've taken that may have discussed the inner product. Right? So we're going to look at the inner product, which will lead through to the concept of length of vectors, angles between vectors, and then this idea of orthogonality. So that's what we aim to build here. Okay, so it's important to realize when we talk about this length and angle, right? These make sense in the 2D and 3D construct of vectors, but all these definitions and these calculations work for any vector in R in n space. Right? So it's a more abstract notion of length, angle, and orthogonality, but we can use that R2 and R3 concept to kind of build our intuition for that. But just keep that in mind, right? When we talk about angle between vectors, then it's easy to visualize in like an R3 space. But what does that mean in like R5, R6, etc. Right? And one thing also, so as we move along here, just understand here that in our textbook, right, all the vectors u, v, they're usually in reference to Cn, the complex space. But for us, really, we want to focus for really uv in the Euclidean space, that being R to the n. Right, so when we are in the Euclidean space, so a vector u, right, which can be, let's say, a plus bi, c plus di. Right, let's say that was u. Okay, so in the complex number space, when we talk about something called the conjugate, that would be a minus bi, c minus di. All right, so you'll see that bar over the vector to signify the conjugate here. So just keep in mind when we are in R to the n, right, that is where we're looking at AB. So the concept of a conjugate does not really apply. It's still AB, right? Since the conjugate is when you flip the sign on the complex part of the number. Okay, so as we define the inner product, we don't really need to worry about those the conjugate portions of our vectors here. Okay, so now let's start by just defining what our inner product is. So you may be familiar with the inner product, like I mentioned earlier. Okay, so the inner product for vectors u, v, element of Euclidean M space, right? We define u, v to be equal to the sum I equals 1 to n of u sub I times v sub I. All right, again, remember those are the elements, right? So again, deciphering this, so we go element wise. So first element in u gets multiplied with the first element in v. Then you add first element, second element in u gets multiplied by the second element in v, and you continue working your way through each vector here. All right, so it's important to realize that a couple things here about this is that the inner product does not yield another vector, right? It yields a scalar, a real number. Okay, now this inner product is properly defined with the properties of scalar multiplication. So what that means, if you have alpha u v, that equals to alpha u v. Okay, and also it is a symmetry, or this commutative property. When we have uv, that's going to be identical to vu. All right, again, we ignore the conjugate part of it since we won't be dealing with any complex numbers here. All right, so these are the key properties of the inner product. We can define other properties, but they're based on this, the definition and the fact that the scalar multiplication and the conjugate symmetry hold here. Excuse me. All right. So now let's do an example to see how this works. Let's say for this example, let's say u is equal to 2, 3, 0, negative 1, 2, and then v 1, negative 1, negative 2, negative 4, 1. Okay, and I want to find u v. Okay, again, we have the definition that uses sigma notation. U sub I, v sub I. All right, and again, the way you want to interpret that is you go element-wise, first element times the first element of the other one, 3 times negative 1 plus 0 times negative 2 plus negative 1 times negative 4, and then plus 2 times 1. Okay, so here we have 2 minus 3, that's 0, plus 4, plus 2. So we get 4, 5, 6, 8, 5. Okay, again, a scalar. All right, so up to now we had not defined what it meant to multiply two vectors, and really that operation was still not defined. Instead, we have this thing called an inner product, all right, where we can kind of think of it. We are multiplying numbers, right, but not vectors themselves, right? That isn't an operation defined for the Euclidean space, right? So the value of the inner product, as we can see, we're just multiplying and adding numbers, so it could be positive, it could be negative, it could be 0. Okay, so here's our basis, our starting point here. This the inner product. From there, we're going to build this idea of the length of a vector, right? And then we'll continue building from there this idea of what does it mean to be orthogonal and what's it mean to be an orthogonal set, right? And all those properties and determining whether something is orthogonal or not, or finding lengths and angles, all of that comes from our inner product here.